All right, so welcome back to the channel here. Again, my name is Joey. I'm going to be your chemistry teacher for this session. Again, just a little brief background about myself. Again, I am currently a secondary school educator, just hopefully getting my Ontario certification, college teacher certification quickly in the next month or so. My specialized subjects are in chemistry, so I teach secondary school chemistry and science as well as in music. But I'm also hoping to get my my math teachable in September as well, following a little bit of learning. So basically what we're going to do today is, if you tuned in previously in my 12 p.m. stream, we did a lot of questions, mostly from grade 11 and below, so some grade 9 science problems and some grade 11 problems as well. And we did like two grade 12 questions when we're talking about Hess's law. We were talking about Hess's law and electron configuration, so some structures and properties of atoms and electrons. So what we're going to do it instead, we're going to jump up a level, and what we're going to do is we're going to start doing kind of the university level chemistry. So either you kind of learn it in particular organic chemistry. So this would be, you could kind of learn this stuff in about either university level 1 in the end of general chemistry, where you do talk about organic just a little bit, and then obviously second year there's organic chemistry 1 and organic chemistry 2. So that's what we're going to talk about for today. We have a couple questions, hopefully 10 depending on what how we do for time. So without further ado, let's get started on some organic chemistry problems here. Okay, so it says my first question. It says, in the reaction box, place the best reagent and conditions from the list below. So I'm going to redraw this, and basically it says here, I have a dibrom. I have a kind of, but this IUPAC name would be what, 2,3-dibromobutane. So that's what I would have here. I would have Br and Br. And what I need is, I want to react it to form kind of this alkene with bromines on each side here. So I have alkene, and this is in a trans type of configuration, right? Again, oh no, I didn't want to clear everything. My bromines are on the opposite side of the double bond, so this is a trans configuration. So it's something that we're kind of familiar with here. So what reagents would get us there? And there's actually a box here, which is nice, to provide us with the best possible solution. So again, what we have here is alkyl halide. Do some blue. We have an alkyl halide. And I want this would be this is something in terms of this would be a alkene with a bromide. So it's also alkyl halide, but you can say it's there's an alkene with two BRs trans to it, right? Again, there's just a trans alkene with two BRs, or two bromines, you say trans alkene with two BRs. So which reagents would get us there? So let's look at the box here. So let's look at, I zoomed in, that's awesome. So what I have here is, again, I have excess NaNH2, which is sodium amides. That's a base, so we can use that actually. That's a great way for us to deprotonate and eliminate our bromines, so it creates a double bond. That's good. BH3THF wouldn't give us with water, it would give us a alcohol instead, so that's not it. NaOH is simply a base, so I would get a hydroxyl group. HBr would just wouldn't do much here. Maybe in the second step it might do something. PBr3, again, you just get selectivity of bromination. It's just a bromination. Lindlar's catalyst doesn't do anything with my alkyl halide with the alkene double bond, because again, that just reduces alkynes to alkenes. Bromine 1 equivalent doesn't really do much here. The acid here wouldn't reduce my base here. It would actually just make an OH group, so another hydroxyl. CH3Br does not react with another. Alkenes don't react with each other. NHBH4 would be simply just a reducing agent. So again, I don't have a carbonyl group here. So the only option here is actually NH2. So this is sodium amide. And what does sodium amide do? It's going to eliminate. It's going to eliminate my bromines here. So if I look at, I can add here this NaNH2. NaNH2. What it's going to do, this is sodium amide. What this does is it deprotonates, or what it's going to do is going to react with my hydrogen. It's going to react with my hydrogen here, right? So I have two hydrogens here. And what it's going to do is I'm going to draw out the mechanism for you. This is a E2 elimination. So it's a E2, which means it's a bimolecular elimination, and this happens all in one step. So basically what this does is the negative anion from NH2 is going to go and attack this hydrogen here. So this hydrogen is going to go this way, and then it's going to kick bromine out, because bromine is going to leave and it's going to get kicked out. And then I am going to form a double bond here. I'm going to form something like this. I'm going to get something like this, and it's going to eliminate one of those bromines, right? So I'm going to get something like, so I would have one. I would have a double bond here. I would get one here, and this would be a Br here, right? So I would get this as kind of my my secondary here. And what I could do is this, again, this is an E2 reaction, right? So I'm eliminating the hydrogen here, the bromine gets kicked out, it's a good leaving group, it's gonna get kicked out, and then it's going to eliminate across this double bond here. So it kind of looks something like this, but I need another Br in this position here, right? So what I can do is, again, I can eliminate again. I can do another equivalent of NaNH2. So I'm using the exact same equivalent. So that's why this is the hint. It says excess NaNH2, right? So in reality, you actually need two equivalents here. So this is NaNH2. And what it's going to do is going to, again, do an E2, right? This minus here is going to attack, it's going to eliminate this bond here on H, right? This H here. And then it's going to, again, what it's going to do is going to go, this minus is going to attack this hydrogen here. It's going to, which then eliminates this bond and kicks out this bromine, right? So I'm going to get now an even different molecule. I get a triple bond, right? I get a triple bond here, and then just basically a triple bond here. So I get it's 1, 2, 3, 4. I get it's still a 4-carbon molecule, but this second bromine got kicked out, and I'm getting a triple bond here. So I have an alkyne now here. This is an alkyne. So that's what sodium amide does in this particular case. Alkyne, and then all I'm going to have to do is the second step, because this is the first step, right? I add NH2, it's going to do an E2 twice, so it eliminates twice. I get an alkyne, so from an alkene to an alkyne, and then what I'm going to do with this one is, how do I get from here to, from this alkyne to my alkene with two more groups trans to it, right? I'm simply just going to have to add Br2, right? Br2 with one equivalent is going to give us, it's going to add across this double bond, and it can add trans to it, right? So again, Br2 with one equivalent of Br2, not two equivalents, because Br2 would add, there's two bromines, which means it will add across the triple bond here. So one equivalent. So what it's going to do, again, it's going to, this minus, bromine has a negative charge here. This bromine is going to attract very much, this bromine is going to basically add across this double bond here, and then I'm going to get a get this product here, because it's one bromine is going to add across this here, one Br here and one Br here, right? And so it's going to get this formation here. So that's what the bromine does here. So again, the answer here is NaNH2 and Br2 here. So let's see, and which is correct, right? So again, they didn't really show their work here. I showed the kind of elimination two mechanism here, and then Br2, it simply just adds to the triple bond, right? And adds trans to the triple bond here. In this case. So that's what we're doing. And that's our question 1. So this is pretty good. This is question 1 for our organic chemistry unit. Simple double elimination. So E2, so this here is a, maybe I'll highlight this in blue. E2 elimination, this here is another E2 elimination, and this is simply just addition reaction, right? Br2 just adds to, it's adding to this triple bond, right? So simply just addition here. So very, very easy in terms of what we're doing here. So that's number 1, so that's good. Yeah, that's number 1 here. So let's look at number 2. So the solution, again, is correct, right? So I can say here that this solution, great solution, but I wish there was more. I wish you showed the mechanism of action, the mechanism behind NaNH2, the E2 elimination, behind the E2 elimination using sodium amide, and the addition reaction with Br2 across the triple bond. But either way, the solution is correct, right? So I'm going to say solution is correct. And that's our number 1 here. Okay, number 2. So let's look at this question here. So here, name and draw and name the organic product of this following reaction. Right? So number 2 states that, okay, so I have a benzene here. I'm going to draw it out this way. And then what I'm going to do is I'm going to react it with CH3Cl, so methyl chloride, and then and then my catalyst here is aluminum trichloride, right? Aluminum trichloride. What am I going to get? And I get some product plus HCl, right? Plus HCl. So I'm again another classic predict the problem in this case. So again, take a moment to think about this problem here. What would this do in terms of when I'm reacting with a aromatic compound? I have benzene, which is very, very, very very stable, but then again I have this AlCl3, right? So what does that do to the benzene? Does it do anything here? So again, think about this problem, and we'll look at it together. So take a minute to think about this problem here. So again, you can think of this as the aromatic compound is very electron rich, right? It has a negative charge here. So I'm looking for a positively charged thing here, right? Positively charged thing here. So, okay, so again, just a little hint about this. So again, what we have here is benzene, and we have CHCl3, right? So again, just a methyl chloride in this case. And then what we want is we want product, right? So this is a classic example of a Friedel-Crafts alkylation. So let me write this down. This is a Friedel-Crafts alkylation. And how do we know it's a Friedel-Crafts? Well, first I have a Friedel-Crafts. Well, the first giveaway is that I have a benzene. If I have benzene, it doesn't really react. Benzene here is pretty unreactive just because it's very, very stable, right? I have here, it's again a resonance stabilized compound. I have delocalized electrons, and what does it mean is that these electrons, these double bonds are, you can think of them as jumping around, but it's aromatic compound. So these double bonds are constantly in motion, and they're very stable by itself. So this is a Friedel-Crafts alkylation, and we know that because there's a benzene, and this is a dead giveaway. The reagent, the aluminum trichloride here, and then this here is what it's going to be. This reagent here is part of the Friedel-Crafts, and it's going to activate the alkyl halide. So what does that mean? What does that mean when it activates the alkyl halide? So what it does is, I'm going to draw the mechanism here. It's going to I have here, again, CH3 is the positive charge, and this is the negative charge here. Aluminum has a positive charge. Actually, let me color coordinate this. Sorry. So this blue is a positive charge, and Cl is negative here. Aluminum is positively charged, and the chlorine is negative. Sorry. Negative, right? So what it's going to do is this CH3 is going to get activated by the aluminum trichloride. So what it does is it's going to do some black. It's going to bond with this aluminum. So it's going to make. Let me redraw my arrow here. It's going to make. Actually, let me just erase this because I'm going to draw the mechanism here. So it's going to activate this methyl group. And what it does, it's going to make something like this. It's going to make some type of this is Cl here. It's going to bond with the AlCl3 here. And what it does is, in this case, this would have now a positively charged chlorine, and then this would have a negatively charged. So this is activated now. This is a big electrophile, right? Because I have here this carbon CH3 here has a oh, sorry, I didn't color coordinate this. Give me a second. This is a positive charge here, and then this would be just the carbon here, and then this is the H3, this is the methyl group, right? And if this here is the positively charged positively charged chlorine here, again, this carbon here is also this here is also positively charged, right? It's partial, it has a dipole, partial positive, right? So what it does is it's going to, it wants to kick this out, right? It's going to this aluminum is going to, it's a really, really, really good leaving group than chlorine. So what it means is it's going to, this is now being activated, right? So this chlorine is simply just going to leave, and then I create something called a carbocation. So what that is, it's simply just a, or sorry, this entire thing is going to leave, because this here, you can think of it as AlCl4, right? AlCl4, this entire thing is going to just get kicked out here. So this entire compound is going to get kicked out. That's what makes it a good leaving group, which means I get H3C plus here. And this here is very, very, very unstable. And because this here is a carbocation, right? This here, it wants something that's negative, right? Carbocation. It wants something that's very, very negative. And the last, where's my negatively charged to satisfy this positive charge? I have a resonance stabilized here, electron rich, right? So I have here a carbocation. It's going to then attack one of these bonds here, and then it's going to make my Friedelscraft product here. So I'm going to draw that. So I made the carbocation, and basically what that does is it's going to, if I add this with my benzene here, and I guess again, the benzene here is electron rich, right? This here is, this here is a positively charged, so it's in blue. A positively charged carbocation. This here is, you can think of it as a negatively charged, because it's electron rich, right? It's negatively charged, so it's going to attack this, and then it's going to make, finally, my product, which is benzene, and it's just a methyl group here. So this is a Friedelscraft classic example of a Friedelscraft alkylation, right? I'm adding an alkyl group to my benzene, right? So classic Friedelscraft's alkylation here. Sweet. So let's look at the product here, and again, it's correct, right? Again, my product here, I put it on this carbon. It doesn't matter. I could rotate this benzene. It still would make this compound here. So again, I don't like how they don't use the mechanisms here. So I'm just saying good solution. However, missing step by step, because it's just to fill in the blank, right? Missing step by step mechanism of alkylation of Friedels, and this is a Friedelscraft, right? So I'm going to state Friedelscraft's alkylation. So the solution is correct. Okay, sweet. All right, this problem is a Diels-Alder. Ooh, this is a fun one, and fun. I mean, it's pretty hard actually. What I mean by fun. So this is my third question here. It says here, draw the correct product for the following Diels-Alder reaction. So I have here, this is a cyclopentadiene, right? Oh gosh. Pentadiene plus another cyclopentadiene. What is that going to give me? Sorry. Pentadiene. Oh no, that's a hexagon now. It's very hard to draw pentagons on my tablet. Okay, there we go. So I have two cyclopentadienes. Again, this is a 5. I'm going to draw this is a 5 carbon ring. 5. Sorry, I'll just write 5. It's a 5C ring. This is a 5C ring. And what it says here, it says draw the correct product for the Diels-Alder. So I know it's a Diels-Alder reaction, right? So if you recall, what is a Diels-Alder reaction here? A Diels-Alder, right? So remember, in a Diels-Alder reaction, we have something called, we need a diene and a dienophile, right? Dienophile. So if you recall, one of us, the simplest Diels-Alder, it requires a cis formation of an alkene. So something like this. Like it's cis right now. It's cis right now. It's the methyl group, or the side groups are on the same side. And then if I add this with just the ethylene, what I'm going to get is a cyclohexene with a double bond, right? So again, this is another form of an alkylation, but it's like, you can think of it as like, we have double bonds and they're electron rich, and they're reorganizing themselves to form new carbon-carbon bonds. So for this mechanism here, what I can do is I can draw, this is electron rich, right? So what it does is it's going to go into this ring here. This ring is going to move this way, and this ring is going to move up. So I'm breaking I'm breaking two pi bonds. I'm breaking two pi bonds, which are these two bonds I'm breaking, and I'm creating one pi bond, right? Which is the product here. I'm creating a pi bond, right? So again, I have three. So I had three pi bonds before. So I'm gonna break two. I'm left with break two, or I can in this case it actually breaks all three, right? I'm breaking this double bond, and this double bond. So I can think of it as breaking three pi bonds, or breaking all my bonds, breaking all my double bonds, and then I'm going to create new pi bond, right? Or just can create a new pi bond, which is this guy here. So how would that relate to this ring here? So again, take a moment to think about this. Where is my diene? Where's my diene file? Because in this case, it's actually the exact same, right? It's the exact same structure here. So which one's my diene and which one's my diene file, right? Where are my electrons? Where are the double bonds going to move? Where are my electrons going? So think about this for a minute. This is actually it's a very, very difficult problem. So think about this for a quick moment, and then we will talk about what product it's going to make. Because again, if you count the carbons here, we have 1, 2, 3, and 4, right? Let me count the carbons for you. We have 1, 2, 3, and 4. This is 5 and 6, right? Which means my product here has to have 6 carbons. So if I have 5, because we're not losing carbons, you can't lose carbons randomly, right? So we have 5 carbons here, 5 carbons here, which means my product has to have 10 carbons, right? It's a 10 carbon, right? So again, what would I create if I were to combine both rings together? So I'm going to give you a hint. 2 cyclic structures, right? I have two. So this is one cyclic structure, and this is another cyclic structure, which means my product, when I combine them both, I make a bicyclic structure, bicyclic structure, right? When we talk about bicyclic structures, they look something like this, right? They look something like this. Hopefully if I draw this correctly, it's not that bad. Actually, hold up. Let me redraw this. Yeah, they look something like that, right? You have something that's sticking up from the plane, right? 1, 2, 3. Again, this is not accurate of the carbons, but this is example of a bicyclic structure, right? Or you can draw something like, instead of a stick here, you could draw like a little V here to say it's bicyclic. It doesn't really matter. I like to draw the stick here because it's pointing up, right? So again, this here isn't 10 carbons here, right? I have a bicyclic structure, but it's not 10 carbons here. So I have 1, 2, 3, 4, 5, 6, 7. So I'm missing 3 more carbons, which means I have to have something here, right? So this is 7, which is I have 8. I didn't want to move this. Sorry, I have 8. This is 8, 9, and I guess 10 would go this way, right? So I have 1, 2, 3, 4, 5, 6, 7, 8. Oh no, this is 9. That's wrong. Sorry. So I would have to go. I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's going to be my cyclic structure. Right? Let me count again just to make sure if I have the right amount of carbons. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 carbons in total. So this here are the bicyclic structures, right? And again, where are my double bonds? Right? Where it's going to go? Where is it going to go? So I told you that it's going to break all my double bonds. It's going to create one new pi bond, right? So if I have, and this here I have 3 pi bonds, right? To break 3 pi bonds, it's going to create a new pi bond. So which means in this case, I'm going to break 3 of them and create a new one. So in this case, my mechanism, I could draw it out as, it doesn't matter which one's the diene and the diene file because they're both the same structure. So I'm going to take this double bond, for example, it's going to attack this double bond here. This is going to shift up. This is going to get out. So which means I'm breaking these two. I'm breaking this double bond here and these double bonds, and I'm going to create one. So the net gain in this case is I'm going to net, I'm going to lose 2 pi bonds, which means I'm going to lose 2 pi bonds. I'm going to make a new bond here on this side of the structure, right? Which means I could write my double bonds like this, right? I'm going to create one new one, right? Remember, if I break 3 and I create one new, the net loss is that I lose 2 pi bonds, right? So that's why I only have 1, 2, and 3, and I'm making one new one, right? And then for this, with this guy here, this guy's not touched, right? So it's not participating in the Diels-Alder, which means this here is on the other side of the cyclic structure. So I can write this. This one would be on this side here, right? So this here is my Diels-Alder reaction for a, this would be a 2, this is a Diels-Alder reaction, alkylation. I'm sorry, this is a Diels-Alder reaction of 2 cyclopentadienes, and that's going to be my answer for this problem here. I'm just going to check if that's correct. And again, they made some sort of I like how they drew the mechanism here. Again, this goes away, this comes in, this comes out, so that's fine. And they get 1 here. They have the point here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, and then I have the double bond here. So they drew it like a house kind of thing. It doesn't matter how you draw it, but I drew it correctly as well. So it doesn't matter as long as it's on the same 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. I believe it's there. Is it 1, 2, 3? 1, 2, 3, 4. Yeah, 1, 2, 3. 1, 2, 3, 4. 1. Give me a second. Let me just count. 1, 2, 3, 4 has a double. 1, 2, 3. 1, 2, 3, 4 has a double. Yeah. So this is the same structure as what they have here. They added heat into 1 to 4 cycles, right? So again, Diels-Alder simply just needs heat, right? So I usually write like a triangle or something like that to prove that this is a Diels-Alder reaction, or I simply say dA or something like that. It doesn't really matter. But again, this syn addition is stereospecific, like all Diels-Alder reactions, right? So I like this solution. This is a perfect solution and great step-by-step showing the mechanism of a Diels-Alder reaction. So this here is correct. Nice. So the tricky thing here is the bicyclic structures. Right? If 2 cyclic structures, it's going to create a new bicyclic structure. So this is actually a very, very difficult concept because it's something that again, it's very, very like this is organic too now at this point. So I'm going to submit solutions correct, which is awesome. Okay, so let's look at question 4. So it says draw the major organic product form in the following reaction. So I'm assuming this is the reaction here, and they drew it out. So let's work out this problem first before I have the answer there, but let me just work out this problem and kind of explain what they're doing here. So let me draw this out. So I have benzene, I have a methyl group here, and then I have some sort of this is a ketone. O, double bond O, and then something like that. What I'm going to do is I'm going to react it with Br2 and acetic acid, CH3COH, right? And then what am I going to get? Again, 1 mole reactant, 1 mole Br2, right? So what the reaction stoichiometry. So it says here, so we have here, this is a treatment of a carbonyl, right? Our aldehyde or ketone with 1 mole bromine in the presence of acetic acid gives us an alpha halo aldehyde or ketone, right? So again here, what it's going to do is going to add to this aldehyde. This is a ketose here. It's going to add to this ketone here. So how do we do this? So again, take a moment to think about this problem. How is this a correct answer? Like, do they have a bromine? How does it randomly just stick on top onto this structure here? So let's think about that for a sec, and then let's reconvene in about a minute and take a moment to think about this structure here. So this is a this here is a alpha halo aldehyde. So what is this? So what does that mean? Here. So let me take a drink of water, and then you can kind of look at the solution here. And if you need help, you can always look at this solution. So what is it doing here? How does this work? So let me draw out the H's here. So let me draw out an H here. That might help you. And let me draw out the charges for you. So again, this here is a negatively charged thing. This here is a negative charge, and this here is a positive charge. And again, this which means this here is oxygen. Again, it's electronegative, so it has a dipole of negative here. This here is a partial, which means hydrogen here is a partial positive, right? Partial positive. So what am I doing? How does this work? How does this work? Sorry. So how does this work? What we're going to do is we have this this negatively charged type of thing here, right? What it's going to do, it's actually going to react with itself. So let me redraw the benzene here. Oh, actually, let me just draw the ketone here. I'm going to say this is the R group, and the R group is just this this methyl benzene we have here. We have this is O, this is an H here, right? So again, what it's going to do, it's actually, and again, this is partial negative, this is partial positive, right? Partial positive. So again, what it's going to do is, again, I have this negatively charged here. What it's going to do is actually going to, it's going to travel here to this this hydrogen, and it's going to then kick out one of these bonds here. So which means I'm going to get something like this. Firstly, so I'm going to get the R group. So let me get the I'll have the R group here. The R group is just the benzene. It doesn't really matter. It doesn't really matter what this is. But I'm going to have a single bond OH here, and then it's going to have. I'm going to maintain this will have a double bond here, right? It's just going to kick out. It's just going to protonate this. It's going to kick out this double bond here, and then I'm going to create an alkene instead of carbonyl, and I have a hydroxyl, right? Again, this is a ketone enol. It's an enol now, right? It's a ketone. Again, if you have aldehyde and ketone, I think we can do something called it's an enolate reaction, right? This is a alpha halo aldehyde ketone addition, but we're using an enol to do that as well. So basically, after that point, we know that this is electron rich, right? So what it's going to do is going to actually let me redraw the bromine here. This here is and it's negative, right? So this here is Br and Br, right? So what it's going to do, again, this oxygen has this negatively charged here. So what's going to do is going to then collapse on itself. It's going to kick the double bond away, and it's going to then, this bromine here is going to come and attach to this double bond here. So what I get here is I get an addition reaction, right? I get something like this. I get R, and then I get here, it's the double bond O. I recreate my double bond because it's the double bond's going to get, the oxygen is going to make two bonds to make it stable, and then I get the bond here, and then bromine is going to come over here, right? Which means I get the bromine like so. So I get a bromine like this. So that's basically the mechanism for this is an alpha halo aldehyde or reaction here. So basically for this reaction here, if I if I do this exact same thing, what I'm going to get is this R group is just this benzene group, right? So the product is going to be basically what you see on the right screen. So let me erase this here. I'm going to get first I'm going to get this enol here. So this is an OH, and I get a double bond here, and then this Br is going to come, or sorry, this negative here is going to collapse on itself, and then the bromine, I'm going to redraw the bromine. Sorry, I'm going to redraw the bromine here. The bromine in black, sorry. The bromine bond bromine. This is going to be here, and then it's going to this here is going to leave. Sorry, this here is going to go this way. The double bond is going to attack this bromine, and it's going to kick out the bromine, right? So so I'm going to get here my alpha halo aldehyde here. So this is 1, 2, 3. Sorry, and then I have here one. I think get back my ketone here, and then it's going to bond Br. So exactly the same as what we did. So this is a great solution. Again, this is my solution here using using an enol as an intermediate. So this is correct here. Great solution. I wish there was a mechanism showing the enol intermediate. Using the enol intermediate. That's what I meant to produce a alpha halo. In this case, it's ketone. Nice, sweet, great solution. Solution's correct. Sweet. So that's number 4. So now let's look at number 5 here. We have IR spectra here. Number 5. Yes, this is IR spectra. And we need to decide which compound matches the IR spectra here. And for some reason, I cannot find the solution. So this is actually I can't verify the solution here, which is weird. But okay, I think we might be able to work with this. I can't verify the solution, unfortunately, which is kind of weird. So I might have to, I can't click next as well. So hold up, just give me a second while we might have to actually skip this question. But let me just talk about this question before I skip it. So this is the IR spectra. So it says here which compound matches the IR spectrum. So it says here, gives us all the options, right? We have 1,5-hexadiene, trans-4-octene, cyclohexene, dipropyl ether, 1-methylcyclopentene, 1-hexanol, hexane 3-ol, and 3-hexanal. Or hexanol, sorry. So basically what we have to do is we have to look at the IR graph, and then we need something, we need a chart to determine what wavelengths and what wavelengths there are, right? In terms of how we read the spikes in the graph. So let me look up IR spectra for you, and IR spectra chart or something like that. And basically it shows you, let me just use sigma L-rich, because this is a pretty good one here. So it's by frequency range, right? Sorry, I don't want to know. I just want a graph. Okay, cool. Sure, can allow. Okay, so it says here, I have a spike here. This is about at almost here. If I look at the graph, I have a spike at about 3,100, and it dips to about 2,900, 2,800. So 3,100, 2,900, and 2,800, right? So it says here, 3,100, I don't really have anything. It says here an amine, but amine here is not a solution, so that's not right. But here it says 27 to 800. Yeah, this is a stretch between, I want a sharp broad, right? So it says here sharp broad between 3,000 and so let's check here. 3,000 here. It's just an alkane in this case. Alkane here with 2,000, 3,000. This here is a medium here. So again, this dip in the percent transmittance in this case, it's a medium. It's kind of a medium dip here, right? And it's just an alkane. So all of these ones here, because it can't be an alkene, right? Alkene would have 3,100 to 3,000, and this here is just below 3,000 in this case here. So it would not be an alkene in this case. There's no really sharp drop here, and the other drops I see are one's at about maybe 1,500, one is at 1,000. So let me just scroll down and look at 1,000, about 1,500 here, and we can basically look at we can actually use a process of elimination, right? So it's the way there's an alcohol, because alcohols would have an OH stretch, right? About 3,700 to 3,500, right? So again, it's not in this graph, so I don't have a hexenol or a hexanol at all as well. So these two are gone. I don't have a dipropyl ether. I don't have, again, ether would have just an oxygen here, and I don't think I have a C bond O. C bond O stretching would be at about 1,200 to 1,275, and this here it's pretty high up here, so it's not a strong drop here, so it's definitely not it. So I can eliminate dipropyl ether and hexanol, both hexenol and hexanol from that from here. So we know we're working with alkyl group, right? It's either a double bond or there is a cyclic group, right? So let's look at what a cyclic group could be. Let's see here. So I want a cyclic group as my, in terms of my compound class. So let me scroll down. It's usually about the 1,000 range here. So let's see, or maybe can I search it? A cyclic group, yeah, cyclic here. Okay, so it says cyclics here. I have one that's 1,650, and that's not it. So it can't be a cyclic alkene. So you can, this 1-methylcyclopentene is not it. And what else? Do I have another one here? Yeah, alkene again is 1,650 to 1,500. So it's definitely not it. So it can't be a cyclic alkene. So it has to be either a cyclic alkane or a straight chain alkene. So let me just control find alkene again, And I have here alkene has a strong bend at 1000 between 995 and 985. There is some type of thing here. So I have here at 1000, there's a little dip here, which is great. And then I have, what else do I have here? I have one that's about 1500 and 1400. So let me just look at, scroll up and just see what would that look like. So it would look at something like this. You would get probably the alkane groups here. So in this case, I would probably think that this would be either, it would have an alkene. It would have an alkene kind of group here for this one drop here, because again, out of 1000, it's a strong sharp at 1 here, right? So this would mean that there's one double bond here, and 1,5-hexadiene has 2 double bonds, so it wouldn't have it would have two kind of peaks at 1000, so that's probably not correct here. So the only option left is trans,4-octene. So trans,4-octene contains a double bond, and it contains and it also contains the other straight chain alkane group. So this one would probably be trans,4-octene. I'm just going to search up cyclohexane here. So another cyclo group here. And I just want to see if they have cyclic alkane. Cyclic alkane. So I don't think they do. Let me just look at alkane here. And let's see if I have, so CH, no, this is a methyl group. I don't care about methyl groups. I care about, no. So they don't actually have a IR spectra for cyclic alkanes. So let me just Google cyclic alkanes. If there's an IR kind of doc here. Again, on a test, you would probably be given all this information. You don't have to memorize all the numbers, because that's kind of, that's very, very much so not the right idea. So let me see cyclic alkanes. So I can't find it here. Yeah, so it's probably not it in terms of the alkanes here. But again, my graph here stated that, again, remember this here is the 3000 to about 2900, 2800 range would probably refer to an alkene here, right? There's simply just the stretch between 2800 and 3000 here. So it would probably be, again, this is the alkane stretch, and 3000, 3100 would be this little dot, the little dip here, right? So it would have something in terms of alkane and also an alkene here. So it'd probably be a trans,4-octene kind of group. So that's probably my answer here. Again, I can't verify this answer, unfortunately, but again, we have to take my word for it, I guess, in this one. So I can't actually exit, click new question. So just give me a second while I kind of get this sorted out. So let me see how I can click forward here. Give me a second. Sorry. Let's see. I can't click forward. So this is weird. Sorry, just give me a second. Yeah, because I can't click forward. So sorry, it's something to do with the system here that it can't really find another question. I might have to actually manually do it. So sorry, just give me a second, guys. Just give me 1 second so I can put some questions up again, because I can't actually click next onto the other slide. So I would have to redo basically, but I have to because I collected a bunch of questions before and I was supposed to click next, but this one doesn't let me click next. So I would have to go and manually input them in myself. So just give me a second. Hold on, guys. I'm so sorry. We have about 15 minutes left. So our spectra was here. So I'm going to do this problem for you real quick. So let me select problems here. I can search this one. I'll probably try to do maybe 3 more problems. Let me select 3 more problems for you. Sorry, guys. 1, 2, and 3 here. So hopefully I can do that. I can select those ones, finish selecting, and this here is I can start this stream here. Perfect. So okay, I got that. This guy got that down, and this is down. Okay, cool. Sweet. So I'm back again. Sorry, I had to redo some of these questions here. So again, I had this question. This is a new question here. It says add curved arrows to the following SN2 reaction. You can't really see the SN2, so maybe I'll zoom in. So it says add curved arrows to this SN2. So we know it's an SN2 reaction, so that's good. We have to figure out we're adding our curved arrows. So what does our mechanism say? So I have here, this is a H bond OH group, and then I have here, this is some H bond C bond Br bond H bond H. And then I'm going to get, this is simply an SN1 reaction here, and I get a substitution. I get OH bond C bond H bond H bond H plus Br minus, right? Very, very classic example of a SN2 reaction. Okay. So again, here I'm adding some curved arrows to this, right? To this SN2 reaction, right? So how would I add the curved arrows here? So again, I believe, oh, this is the answer here, right? So let me look at the answer here. So again, here, minus here is good. I have an electrophile, which is the OH group. It's going to attack the positively carbon, right? I have here, again, here, this here is my negatively charged ion here. So this is a good nucleophile. And again, this here is my bromine, is also partial, it's not negative, but it's partial negative. And this here is a partial positive, right? So what it's going to do is one step, it's going to, this minus is going to come to this carbon, attack the carbon, and then it's going to kick the bromine out, and then I'm going to get this this product here, this alcohol, right? So I have a hydroxyl group, I have an alkyl bromide in this case, and then I'm going to make an alcohol, right? And then Br minus is simply just the side reaction here, and Br minus is the side product here. So that's good. That's the question one here. I'm going to get this. So this curved arrow is indeed not correct, because I need to, for this one I would need to it actually attacks this this carbon here, right? It attacks the carbon and not the hydrogen here. So this question is kind of misleading, right? This negatively charged is attracted to this partially positive carbon here, not the hydrogen here. So that's kind of incorrect here in this case in terms of the diagram here, but I'm going to forgive it because that wasn't the question. And then this is another one. So I have here, this is H3C bond CH2 bond. I have a Br here, and then I have, this is another, this is OCH3, right? Okay, so this is this here is a negatively charged compound here. So I'm gonna do that in blue. This is negatively charged. Again, bromine here is negatively charged, and this, which means this carbon is partially positive, right? So again, what it's going to do, it's going to, this is again, it's another SN2, right? This O oxygen is going to come attack this carbon here, and it's going to kick out this bromine. So I'm going to get a H3C that's not affected here, and then I'm going to get this is a CH2, and then this here would be an OCH3 would be my answer here, and then I get bromine as the side product. So again, this here is a one-step reaction, right? SN2 is a bimolecular reaction, and it takes one step, right? Backside attack, inversion of stereochemistry, right? So you get an SN2 reaction, and it's simply just a substitution between bromine using this here would be a OCH3 group. So it's a very strong nucleophile. So again, one-step reaction because it's strong, good leaving group, and it's a strong nucleophile. Sweet. And then let's do this last one here. I have, let's see. I don't like the way they draw these ones, but it's okay. HCH3, I have one carbon in the middle. I have CH3, I have Br on this side, and then I have CH2. Oh, okay, I have CH3, right? Okay, that's fine. They drew the hydrogen here, right? And then plus I have another OH, right? OH here. And then what am I going to get? So again, here let's label my charges. I used red as negative, right? No, or use red as positive. So negatives would be, this here is I have a negatively charged nucleophile here, and my bromine here is negatively charged, which means my my carbon here is partial positive, right? Partial positive here. So what's going to happen is this negatively charged, or sorry, I was going to do this in red. My bad. This one here is in red. So what I'm going to do again, this negatively charged, or sorry, this is positive. What am I saying? Carbon is positive. Okay, so what's going to happen is this negatively charged nucleophile, strong nucleophile, is going to come and attack. It's going to come and attack the positively charged carbon here, and it's going to get some type of substitution reaction, right? However, what they have here is something that's different. They have this solution is super weird. It says I get a double bond on the carbon, but that's an elimination, and they get H here. So this is an E2 reaction, not an SN2. Oh, I didn't read the question. Sorry, this is an E2 reaction. So E2 is different, right? When we talk about elimination or E2 reaction, again, it's still one step, but it's an elimination, right? So in this case, elimination, what it is this hydrogen is basically what this happens is this oxygen here is going to attack this hydrogen, and then this is going to collapse here, and it's going to kick out the bromine. So how that happens is, and then I'm going to create a double bond. So it's going to create the thing I have on my left hand side, and I get water, right? This hydrogen here becomes bonded to this OH group here, so I get water here. So this is an E2 reaction. Sorry, I didn't look at the problem here. So the first two were SN2 reactions because I am substituting my Br group for the OH group or the OCH3 group, and this here is an E2 reaction, right? Again, my negatively charged is going to attack the hydrogen of the carbon next to it, and then it's going to create a double bond basically right over here. So I'll do that in red. It creates a double bond right over here to make the double bond CH2 here. And this bromine gets kicked out, and I get the water here, and I get H2O, and I get Br minus, right? Because again, the bromine doesn't have anything to bond with here, so these are my side products, Br minus. Okay, so that's correct here. So let's see. I get CH3CO. So this is correct. These two are correct. Negative charge attacks the carbon here, and then it's attacking this carbon, not this hydrogen, and then it goes out. That's fine. This is a E2 reaction. So E2 is going to so the bromine's going to leave first, which is fine, and then it's going to attack, right? So again, this here is that actually this is an E1. They're depicting an E1 here because E1 would be two-step, right? I need a formation of a carbo cation, which is this first step here, and then it becomes elimination. But this here is actually this here is a SN1, so this is not a correct solution here. Do you see what's wrong here? I have a carbo cation. It's creating carbo cation in the first place, which means I have either a E1 or SN1, and the hydroxyl group is actually going to attack this positive charge. So it's going to actually add. So it's a substitution. This is an SN1 reaction, but here I have an E2 reaction. So this is a wrong solution, actually. So these two were correct, and this bottom one here is wrong. So I'm going to say the first two solutions were correct. The third solution is incorrect because it depicts this would be an SN1 reaction because I have formation of carbo cation and then nucleophilic attack, while the question was asking for a elimination in E1 reaction. So again, elimination E1, if I were to draw out the mechanism and draw out the, or sorry, this was the E2, right? This is E2, not E1, E2, my bad, for an E2 reaction. So one step process here. So the third one here is wrong. So I'm going to say the solution is incorrect in this case. So let me do this last problem here. So it says here, let me Let me just do one last question. So I've only done, how many questions did I do today? I only did 6, unfortunately, but it's okay. It's because I had some technical difficulties. It's totally my fault. It's just the question was really weird and I couldn't click next for some reason. I don't know why. Okay, so it says here, draw the organic or inorganic products of the following acid-base reactions. So I have here, this is a ketone here, and then it's a propanone, propan-2-one, and then I'm going to have, this is H3O+. So H, and H. And I'm going to draw my positively charged as red. So this is positively charged. This here is also positively charged. This here is negatively charged. Okay, so what would I, oh, actually, no, this here is not even a dipole. This here is actually just straight up positive, right? Because H3O+ is positive. Okay, so what I'm going to get, organic or inorganic compounds. So basically what's going to happen is, again, this oxygen here is going to grab one of these hydrogens, right? So it's going to make a intermediate like so. So again, here, this minus is going to, it's going to grab one of these hydrogens, right? Because this here is unstable. They both attract each other, right? So I get something like this, okay, OH2, and this is positive here. This here is red. Here's positive, and then what I'm gonna get is I'm going to get this is the intermediate here. And then what happens is that this thing means it's going to be a good leaving group, and then this OH here can either reduce this can get kicked out and be reduced by an alcohol here. So I would get some sort of alcohol, and this is here is correct, right? I get some sort of alcohol here, or here's water, right? This here is water. So I get some sort of OH group. I don't actually have another reactant for it to leave. So I guess it just stays like this is, it just stays like OH2, right? Because I don't have another thing here. And this is in equilibrium, right? This is not stable. And because this this group is not stable here. And this, because I took one of the hydrogens here, I just get H2O. So that's going to be my solution for this problem here. So it's not very like this, these questions here, in organic chemistry, all you're doing is you're looking at where are the electrons constantly moving, right? So where is the negatively charged atom, and where is it going? So in this case, again, it's going to attack this hydrogen here, right? This hydrogen here is positively charged here, so it's going to kick something out, right? So again, here, the arrow is going to attack this hydrogen here, and it's going to kick out the hydrogen. So it's going to steal a hydrogen from the H3O+ to make water, right? Because if I take this hydrogen off, I get from H2O+, I get H2O, and it's simply just going to attach to this here, right? Remember, the negatively charged electrons are always the ones that are moving, right? I'm drawing always from the negative charge to the positive, always when we're drawing the curved arrows, right, for the mechanisms. So I get this this kind of formation here. I didn't draw the H here like so, but this here is the exact same thing, right? I have double bond with OH2 here. So this here is my answer for this problem here. If I were to extend this problem, say if I were to react it with something else, like a strong nucleophile or something like that, this here would be a great leaving group, and it would either go, it would probably go SN2, just because if I have a super strong nucleophile and a good leaving group, it's going to be a bimolecular reaction, one-step reaction, SN2, backside attack, invert, and it causes inversion of stereochemistry, and I get a substitution on this carbon here, on this carbon here, carbon 2. So that's all I'm doing for these questions here. Again, I've run out of time, unfortunately, for this problem. I'm so sorry for the technical difficulties before, but I'm going to see if I can try to get that fixed in terms of what that problem was. So I'm going to say this here: solution is correct. Good drawing of curved arrows to depict electron movement. So MC solution here is correct. So unfortunately, I don't think we have time for this problem, but I'm just going to walk you through this actually real quickly before I go, but I won't maybe we'll leave off with this question here. So we'll leave off this question we're going to leave off. I'm going to do this on Thursday as our first question. But just to get our head around this problem, again, we have an alkyne here. Let me zoom this. We have an alkyne, the C triple bond C. I have a sodium amide as our base here. Remember, we use sodium amide in our first problem, and we have CH3, CH2, CH2Br. Right? We have this is a propyl bromide group, right? So something like an alkyl bromide group, and it has one equivalent here. So what it's going to do, again, sodium amide is going to create a strong nucleophile. It's going to reduce that alkyne into its negative form, right? So it's going to be C triple bond C, but it's going to have it's going to take away that hydrogen on this left hand side on this left hand side here. So it's going to create a negative charge, which means I can do an alkylation with the propyl chain. So it's going to connect there, and then I'm simply just using Lindlar's catalyst H2 to reduce my alkyne into some sort of alkene, because again, Lindlar's catalyst only reduces from alkynes to alkenes, and then H2O and H3O plus is simply just a hydration reaction using Markovnikov's rule. So it substitutes the hydroxyl group onto the carbon that's connected to the most carbons, which is carbon 2. So I'm going to draw that out for you next time, and I'll show you how that looks like. And yeah, that's going to be my video for today. So again, thank you for watching. Thanks for tuning in to OneClass here. If you like these videos, again, keep subscribe to the YouTube channel and definitely keep up with the work that's being done there. But until next time, I'll thank you for watching, and I'll see you in the next video. So take care.